Hey everyone, and welcome. Today, we are going to crack the code on a seriously powerful visual language. It's one that can tell these epic stories of journeys, races, even bouncing balls, all without a single word. Yeah, we're talking about the secret language of motion. Let's dive in.
Really think about that for a second. A car speeding up, a cyclist who decides to take a break, an object just falling through the air. How on earth could you capture all of that action, all that drama in just one single silent picture?
Well, the secret is motion graphs. They literally transform movement into this language of lines and curves, and once you learn how to read them, you can see the story of pretty much any journey unfold right there in front of your eyes.
Okay, so let's start with the most fundamental kind of motion graph. You are going to be amazed at just how much information can be packed into one simple-looking line. So this is our foundation. It's called the displacement time graph. Now, displacement is really just a fancy word for how far something is from where it started. So you've got the vertical axis showing that distance, and the horizontal axis just tracks time. It sounds simple, right? But the real magic is in the line that connects them.
So, if you remember one thing, remember this. The slope, or the gradient of that line, tells you the velocity. A gentle slope, that means a nice leisurely pace. A super steep line? Oh yeah, that object is moving fast. The steepness is the speed.
And check out how perfectly this breaks down. If the line is totally flat, horizontal, its gradient is 0, which means your velocity is 0. You're standing still. But if it's a straight, sloped line, the gradient is constant, which means you're traveling at a nice, steady velocity. Okay, let's put this into practice with a real-world example from our source material. We've got a cyclist's trip broken down into 3 super simple stages. They ride out, they take a rest, and then they ride back. It's a simple story, right? So let's see what it looks like as a graph.
All right, we have the story, and we have the rules of the language. Now it's time to put them together and see how this graph can perfectly capture every single moment of the cyclist's journey.
And here's where it all just clicks into place. On that first leg, the gradient of the line gives us a velocity of 15 kilometers per hour. During the rest period, the line is flat, so 0 velocity. But on the return trip, the line slopes downward. That negative gradient means we have a negative velocity, in this case, negative 20 kilometers per hour. The cyclist is moving just as fast, maybe even faster, but in the opposite direction, back towards home.
This is such a fascinating point from the source. Because the cyclist ended up right back where she started, her total displacement is 0. And that means her average velocity for the whole trip is also 0. But she clearly moved. Her average speed, which is the total distance she covered divided by the time, was 9.2 kilometers per hour. It's 2 completely different ways to tell the story of the very same trip.
Okay, so moving at a steady pace is one thing. But what about the real world, where we're always speeding up and slowing down? For that story, we're going to need a different kind of graph.
So, meet the velocity time graph. This time, that vertical axis is showing speed, not position. And this graph, it holds 2 really powerful secrets. First, its gradient doesn't tell you velocity anymore. Now it tells you acceleration, which is the rate that your velocity is changing. And second, the area underneath the line tells you the total distance traveled.
Let's just lock that in for a second. With this one single graph, you can find out how an object is speeding up or slowing down just by looking at the slope. And you can figure out the total distance it covered just by calculating the area under the line. It's just incredibly efficient. So let's take a look at that car journey from our source. The graph of its velocity would show a line sloping up in section A, which gives us this positive acceleration of 1.5 meters per second squared. A flat section in that same graph would mean 0 acceleration, a constant speed. And then in section D, you'd see the velocity line slope down sharply as the car brakes, giving us the negative acceleration, or deceleration, that you see right here.
Now, for that second secret, the area. We can actually calculate the distance traveled in each section just by finding the area of the shape under the line. Section A is a triangle, covering 75 meters. Section B is a simple rectangle, covering 150 meters. So by calculating the area for each little segment of the journey, we can add them all up, and we find that the car traveled a total of 675 meters. We figured all of that out just by looking at some simple shapes on a graph. That is the power of this visual language.
Okay, so we've got a handle on position, velocity, and acceleration. Now it's time for the ultimate test, a bouncing ball.
This one single action combines absolutely everything we've just learned.
A bouncing ball seems pretty random, doesn't it? It's accelerating, it hits the ground, it instantly reverses direction, it slows down as it goes up. It's just a mess of motion. But when we translate all of that into the language of graphs, a beautiful, predictable pattern just emerges from the chaos.
It's honestly fascinating how each graph tells the same exact story just from a different angle. The displacement graph shows the height of each bounce getting smaller in these perfect little parabolic arcs. The velocity graph shows a constant downward slope, that's gravity of course, which suddenly flips from a negative to a positive velocity the very instant it hits the ground. And the acceleration graph? It's pretty much just a boring flat line at negative 9.8 meters per second squared, because gravity's pull is always constant.
And this shows us perfectly why those bounces get smaller over time. The source material points out that a ball dropped from 4 meters high only rebounds to 1.76 meters. And why is that? It's because energy is lost as sound and heat with every single impact. You can literally see this energy loss in the shrinking peaks of that displacement graph.
So, we've decoded the motion of cyclists and cars and bouncing balls. But here's the thing. This language, it's not just for physics class. Once you learn to read a graph that shows change over time, you start seeing these stories absolutely everywhere. The slope of a stock chart tells you how fast its value is changing. A climate graph shows the rate of temperature rise. This is a universal language for understanding how our world works.
So the next time you see a line on a chart, don't just see a line. Try to see the story that's inside it. See the velocity, see the acceleration, and listen to the secret language of motion telling you its secrets. What stories will you discover?